Welcome back to Cloud 42, I'm James. This video is part 6 of the hand scraper build series. As promised, we'll be making something to protect the insert on the end of the scraper, and also as promised, I'll be using the word ninja several times. I took this scraper into my day job last week and showed it to one of my coworkers, and he was really a little bit dismayed that I was carrying around a tool with a carbide insert on the end with no protection. He's really worried that it would get chipped, and you know, he's right. These things are expensive, and carbide is hard. One roll off the bench, or you know, bouncing against another tool in a toolbox or in a drawer, and I'll be buying a new insert or grinding away a tremendous amount of carbide. I'm not really sure which is worse. His suggestion was to 3D print a cap for this. And I was thinking about exactly how to do that and realized this is the perfect application for flexible filament. This material is called NinjaFlex. This is a thermoplastic urethane, and this is 3mm, and it's about 85 durometer, and it's a flexible, you know, it's a urethane rubber. And I'm sure I'm going to get comments about the fact that urethane is not rubber, but that's fine. Go ahead. But this stuff is pretty neat material. You can use it to print flexible parts for all kinds of situations. I've actually used a dual extruder and printed a urethane tire on an ABS hub just to see if I could do it. And this stuff adheres to everything, and it made a really nice part. So I think this would be the perfect material to use to 3D print a cap to protect the end of this. I can design it so that it fits over, even maybe have a little bit of hook or some compression or something to grip onto the screw so it doesn't fall off. Let's go into Fusion 360 and design a cap. Okay, this is the business end of the scraper. We've got the shank, we've got the clamp, carbide insert, and I've got the screw and the washer all modeled here so that you can, so we can actually see everything that has to go inside a protective cap. Now, there's lots of ways to model this, and I've tried a few of them and played around with it and found one that I really like that's probably the most efficient way to model this, and I thought I'd show that. I've played around with like putting sketches on the side and extruding around this and actually trying to build everything up from scratch, and decided that ultimately that's more trouble than it's worth. And what we're going to do instead is we're going to use the shell command. Now, shell allows you to take a solid, mark one of the sides that you want to be open, specify a wall thickness, and it will then build a shell around the shape that you specify. So the first thing we need to do is actually model up a plug that is the size and shape of the volume that we want enclosed inside the cap. So I'm going to do a couple of things here. I want to be able to make this parametric so that I can modify it later. So I'm going to add some parameters here. Here's my parameter window, and I'm going to add a couple of parameters. First thing I want to add is an offset, and I'm going to do this in millimeters because I'm modeling this up for 3D printing, and my intuition for metric is a whole lot better in the 3D printing realm. And so this is going to be the spacing we want around the outside. And I think 0.5 millimeter should be fine. In fact, I'm going to change the whole document setting thing over here to millimeters, just to make this a little bit easier. Okay, and then we also want to set up the wall thickness. I'm going to go ahead and set a parameter for that as well. And let's make that one 2 millimeters. So these are the basic parameters we need. The spacing on the inside of the cap, just to give us kind of room to make it fit easily, and the actual wall thickness. Okay, so let's create the solid that we want to extrude around. And to do that, I'm going to construct a mid-plane through the middle of the part. So that gives us a place to put our sketch. And let's create a sketch on that plane. Okay, now I need some reference points so I can draw this in the right place. So what I'm going to do is I'm going to do intersect. And so I'm going to do a project intersect, which will then allow me to pick some of these lines that go through that plane. And when I click, it creates a point at that intersection. So I'll just go ahead and pick kind of the key edges here. And that gives us then a series of points that we can use to sketch out the profile for the solid. So do a line, and I'll just kind of connect the dots. Now I want to leave a little bit of extra space in the end there, so I'll leave a kind of a point on it. And we'll bring this back here. And bring this point back to here as well. Okay, now those 2 points, we want those to be vertical, so click those. Oh, I managed to get, there we go. So now those are aligned vertically. Okay, now then down here, I want to actually set this up so that this is symmetrical, so I'll just select both of these lines, click equal, and then this can move in and out to set, you know, how much room I want to have in the tip of this thing. And I'll just go ahead and dimension that so that it ends up fixed. Hello. What's going on here? Control click, D for dimension. There we go. And 0.5 millimeter seems fine. Okay, that gives me plenty of space. And let's go ahead and dimension this as well, just so that we have this controlled. And that looks fine. Maybe a touch more. We'll play with that in a little bit and see how that looks as this works out. Okay, so now I've got kind of a line around this, but that line is in contact with the volume that I actually want to enclose. So let me offset that line by our fit thickness, or the fit offset, and that'll give me a volume that's just slightly larger. And close it, and stop the sketch. Okay, so that now gives us the volume that we want to enclose. So let's extrude it. And I'm going to do this 2 sides. Now I could do it symmetric. I actually do want it symmetric. However, if I do it 2 sides, then I can actually use the object itself. So I say to object, pick a point on that surface. We're going to be creating a new component here. And then I actually, though, then want to offset that by our fit thickness, so that it'll stick out just slightly further. And I want to do exactly the same thing on the other side, to the edge, plus the fit offset. Okay, so now what we've done is we've created a new solid that actually encloses the, this new solid represents the space that's going to be inside the cap. So let me turn off a few things here just to get them out of the way. Now I'm going to leave the screw for a moment because I actually do want to use that. Now we've got this so it'll enclose the scraper. We also want to enclose the screw cap as well. So let's create a sketch on the top here. And let's project the shape of the screw just so that we have that. And then we'll offset that as well by the same, you guessed it, fit offset. And then I also want to enclose a volume that'll allow the screw to come out of the cap. So let me go ahead and stretch this out. Now I'm intentionally making those so they don't come tangent, so they're easier to select and make tangent. Okay, so now let's extrude this volume up to cover the screw. And let's extrude that to one-sided to an object, to the top here. And you have to, the chain faces, you have to specify whether you want it completely enclosed or you want it to go outside. Since the extrusion is actually going to go outside what we selected, we select this. Again, we want to join. And we want to join this component. And so we've got it up to that surface, and then we'll offset it again by the fit offset. Okay, so that gives us the volume that we want to enclose inside. Now let me turn that off to make sure we've got this. Yep, so let me turn off the insert as well. Okay, so this is the actual volume that we have that we want to have enclosed inside of the cap. Change this name. Okay, so now the magic. Select the surface that we want to be open and say create. Is it modify? It's under modify shell. And we want the direction to be outside, and we want the thickness to be the wall thickness. And now what it's done is it's created a shell that encloses the volume of the solid that we had specified. Now if you say inside, it'll take the original volume and then create a shell on the inside that's smaller. So that's if you want to specify the outside and then make it into a shell. But in this case, we want to specify the inside volume. So I say I want to shell it to the outside by the wall thickness. And there is our basic cap. And if I turn a few of these things back on, then we can see how all of that fits. And in fact, let me do a section analysis here so we can take a look. And you can see that what we now have is a cap that fits around the outside of that volume with the offset of 0.5 millimeter that we specified. And we can change that easily by going back and editing the parameters. Now you'll note that I didn't worry about the washer, I didn't bother modeling a little step for that, and we just won't worry about that. It's not enough to worry about. And if anything, because we're using a flexible material to print this, it'll give us a little bit of expansion on the inside that'll actually make it stick on a little bit better. Okay, the last thing we need on the inside here is something to retain it. So I want to put a little step in the top, kind of a little latch of some kind. And let's go ahead and create a couple parameters to control that just in case we want to change it later. Okay, so latch height, let's make this, I'm just guessing, 1.5 millimeters. And let's do thickness. And again, let's just pick something 0.5 millimeter. Okay, now what I'm going to do is sketch it on this surface and extrude it across. So let's create a new sketch here. Now I need it to reference on the front side of the screw, so I'm going to project P, the screw dimensions, onto that. So now this point is the front edge of the screw. I'll go ahead and just draw a vertical line from that to give me a reference. And let's draw what we want here for the latch shape in general. Okay, now I want this to be symmetrical, so I'll just pick these, say equal, and then dimension this up. Okay, so this is going to be the latch width, or thickness. And from here to here is the latch height. Okay, so that gives me a little latch in there. Now I think that looks a little wide and shallow. Let me narrow this whole thing up a bit, and if I go back and edit this, I can just do it by changing this parameter. So change that to 16. Let's go even a little bit further than that. That looks better. You know what, I think I'm going to go even further. So what we're doing is we're making the whole cap shorter. Yeah, there we go. So that'll give us a nice sharp little step there. And let's just extrude that across. And we'll just say to this other side. Okay, so now if we take a look at this in section, you can see we have a little hook now that's going to go over that screw and hold it on. Okay, a few more things we want to do. I would like to strengthen the back edge of this and put a little rib on it. So let's, again, create a couple parameters so we can tune these later if needed. And let's do the rib width, and we're going to make that, let's say 3 millimeters. And then let's do a rib thickness, and say maybe a 0.5 millimeter. Okay, so to do this, we'll just put a sketch on the back. We will hit O to offset this edge. The rib thickness. Okay. And then we'll just extrude that. And that would be minus the rib width. Okay, and now I've got a little rib on the back. Great, now let's smooth a bunch of this stuff out by adding some fillets. Okay, we'll fillet, fillet, fillet. Let's make these maybe 2 millimeters. Yeah, that looks all right. Now let's fillet these edges. We'll get 2 millimeters on those too. There we go. That looks pretty good. Let's add one more in here. I do a millimeter there? Yeah, that looks pretty good. Okay. I think that's all we need. Let's do one more check with the section to make sure that that all looks right. Yeah, I think that all looks right. Let's print it. Okay, we'll click Make and choose the item that we want to make, and this will send it to Simplify 3D. Okay, so we can't print in that orientation or we will have a real mess. So I will hit Control L and select a polygon on the bottom, and that will stand it up, center and arrange. Okay, let's look at process settings. Now, ultimately, we're going to print this on my 8-inch printer because that's the one that I have set up with 3 millimeter filament, and so that's what I'm going to use for the 3 millimeter NinjaFlex. Layers, we're going to run the first layer very, very slow, layer height 0.2 millimeter. And let's talk about infill. We're going to run 50%, and that's fine. The wall thickness on this is not very thick, so it doesn't matter very much. We could even run it 100%, but 50% is just fine. The most important thing here, though, is the speed, and we're going to run 900 millimeters a minute, which is really, really slow. It typically would run more like 6,000. This is a lot slower, and the reason that we have to run this slow is because this NinjaFlex flexible filament is not only really flexible, it's also really highly compressible. And so if you cram a whole bunch of it into the hot end at once, it doesn't necessarily do you any good. All it does is compress the filament up behind the melt chamber and put more pressure on it, but you don't, it's because it compresses, you don't get the hydraulic pressure at the tip as quickly. So as a result, you just have to run a lot more slowly. You push more filament in there, it's just going to come out the tip more slowly than you could force it out with another material like ABS or PETG. So we're going to run it nice and slow. Let's slice and see what we did. The other thing about this is, again, because it's highly compressible, it's hard to prime the nozzle off the edge of the glass and just wipe it off clean. So I'm actually printing these loops to prime the nozzle around the side before jumping in to actually print the cap itself. Now, in this orientation, the cap is going to adhere to the bed, and then it's going to be fully supported up the sides here. and I'm just checking to see if we have any severe overhang. So as this top closes up, it's going to ramp in right here and then get pretty narrow, probably less than 2 millimeters before it tries to bridge over the top. I think that's going to print fine without any support. The rest of this ramps in slowly till we get to the top. And it's the same thing. It narrows at an angle and then closes suddenly and bridges over. So I think this is going to be fine. Let's save this to disk and send it to the printer. I'm printing this on an 8-inch Prusa i3 variant. This one uses aluminum extrusions and wheels, but it's similar to pretty much any kit-built Cartesian 3D printer on the market today. The NinjaFlex filament will stick to almost anything, but I usually use glass coated with a little bit of hairspray. The bed's also heated a little bit, maybe 40 degrees Celsius or so. That's plenty. Like I said, it sticks to just about anything. In fact, if you use too much hairspray or you run it too hot, you'll have a terrible time getting it off. I've actually broken glass trying to get NinjaFlex parts off of the bed. Flexible filaments can also be very difficult to feed reliably, depending on the printer. In this printer, I'm using my itty-bitty belted extruder design with one of the CNC hob bolts that you've seen me make in a previous video. This extruder is designed with very little open space around the feed path, so it confines the filament pretty well, and it does fine with the flex filaments. If you have any open space in the compression portion of the feed path, though, this filament will just force its way out into any opening that's available to it and jam up and cause all kinds of problems. It's also really key with NinjaFlex to print slowly. I'm printing this at about 15 millimeters per second. By comparison, I usually run ABS at 100 millimeters per second. But if you try that with NinjaFlex, this stuff is just going to compress up in the feed channel, and you don't get the hydraulic pressure you need to extrude it through the 0.4 millimeter nozzle. And you just can't get the material out fast enough, at least until you finish printing, and then it just continues oozing for several minutes and piles up on the glass and makes a mess. It's also a good idea to only try to print one part at a time with this flexible filament and keep the non-printing movements inside of the part profile. That's usually a setting in the slicer. This stuff is really stringy, and if you try to print multiple parts at once, they just end up connected together with hundreds of little polyurethane hairs. That's fun too, but it's not really what I'm looking for today. Well, here is the part right off the printer. I'm very happy with how this turned out. Of course, you can see the layer lines because it's a 3D printed part, but it's sealed up beautifully. I always love how this NinjaFlex prints if you can get the printer tuned to do it. Now this is, again, it's a flexible material with a 2 millimeter thick wall. It's fairly firm, but you can see it's easy to deform, and it's a nice flexible part. So the little hook that we have in the top here should be able to flex very easily to fit over the screw. And let's see how it fits. Oh, that is just beautiful. It's on there. It's a relatively tight fit. It fits firmly. It's not going anyplace, but it's not coming off at all. You can see it's hitting the ramp on that screw, and the ramp's holding beautifully. But I get a little tug, and it just flexes and comes right off. Well, I am very happy with the way that fits. Next thing we need to do is finally make the insert that goes in the end of the handle, and we will work on that next time. If you're enjoying these videos, please give me a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching.